Good, thank you very much. And as you probably know, there are two programs at the same time, and one of them has large deviations in the title, and the other one is about tensor networks. So what I'm trying to do here is, not connect that, but discuss some methods, tensor network methods that emerged in the study of many body quantum systems as applied to sampling rare events, rare trajectories, large deviations, and beyond. So for the experts on tensor networks, nothing that I will say is too complicated methodologically. And the only thing I would say is that sometimes when you apply a method to a different class of problems, you see new things just because you're taking a different perspective. Maybe that's the case. So all I will talk about is these relatively standard methods applied to problems, many body, problems which are many body, which are large, where, as we've heard, are difficult to calculate, large deviation, sample, etc. Using these methods, which I'll try to convince you are pretty efficient. So what I'll talk about is, this is more or less the plan. I'll talk about one-dimensional systems first, where the tensor networks are matrix product, called matrix product states. I'll show what they are in a second. Talk about large deviations, that's long time limits, how to sample, the sampling problem that David was talking about, how to optimally sample, that's the word dub there, and how also to go to finite times, which is more difficult than long times because you're away from large deviations in time. And this is work with my student Luke Kauser and Mari-Carmen Bañuls, who's in the other and it's sitting in the audience, and she's in the other program because she's an expert on tensor networks, and it's these papers, and yeah, so is that papers, those papers. Then most recent work, which is from yesterday in the archive, also with Mari-Carmen and Luke, is about the same but in 2D problems. And then you have to move to a slightly more complicated class of tensor networks, these projected entangled pair states, PEPs, as they're called. And if there is time, I'll end up by thinking about the existence of topological phases in the dynamics of classical stochastic problems, the SEP in particular, and that's work with Frank Polman from TUM, this earlier work from this year. It's reviewing a few papers, but the main ideas are simple, and I won't go into them. I'm happy to discuss details. The idea is not to discuss any of the details here, but just to convey the same, the basic concepts. So that we're all on the same page, you've heard about large deviations, certainly from Rob, and earlier today, and certainly just now from David. But let's fix the notation. I will use the language of continuous time Markov processes, but nothing it's easier to derive the things I want to discuss in that context. But this also applies to discrete time Markov processes, to diffusions. Then you can translate it to open quantum systems, but obviously we won't talk about that. So a trajectory omega is a sequence of jumps between configurations, which are calling x, that happen at random times. So you go from configuration x0 to x1 and so on. And then if you want to understand the statistical properties, as we've heard, you want to define observables, functions on the trajectories themselves, which are, the ones that restrict to are time integrated. So you have a trajectory, you have a function that makes the trajectory into a number, or maybe a collection of numbers. And those will be the quantities of interest. So we heard mostly about time integrated currents. That's appropriate time asymmetric observables in non-equilibrium states. And also, David introduced the time symmetric ones, like dynamical activities or frenesí, as Christian calls it. And then if you want to do statistics, what we just heard, you can think in a microcanonical way, if you want, where you look at conditions and trajectories, and that's thinking about the probability of the observable taking a certain value. Just, the probability of the trajectory is a delta function that on that trajectory, the observable takes that value. It's a condition. You fix the value. Or alternatively, under reasonably general conditions, you can think in terms of the corresponding moment-generating function, the Laplace transform of that object. The delta becomes an exponential, and rather than fix the actual value, you fix the average, and you control it with a conjugate field, it's calling S, and calling S there. As we've heard, At long times, these functions have a large deviation, obey the large deviation principle. Time pulls out, they become exponential in time, and their shape is controlled by a corresponding large deviation function, either the so-called rate function we heard about before, or its conjugate, the scale cumulant generating function. So now, I'm calling this thermodynamics of trajectories because this is essentially the structure of equilibrium ensemble method in StatMech. Except that now what we have, the objects rather than configurations are trajectories. So you have ensembles of trajectories, and then you have the basic ideas. You have some parameter that controls the size of this object. In this case, there is volume, but there's also time. In the large time limits, the order parameter distribution or the partition sum become exponential in the large parameter, like exponential in volume. They are controlled by entropy densities or free energies, is what they are. And they are connected by a Legendre transform. So it's essentially the same, the same structure. So if you want to do an analysis of dynamics, it's natural to do, because we have so many tools and intuition from StatMech, is to use a StatMech approach to study trajectories. Yeah? Okay, so what I want to do is I want to compute the statistical mechanics of trajectories for many body systems whose state space is large, and where one of the quantities of interest is the size of the system, and therefore the state space grows exponentially in size and makes the problem complicated. Okay? So typically I want to calculate partition sums in StatMech for free energies in the large size limit, in this case in the long time limit. If we know the free energy, we know about phases, we know about phase transitions. So key thing is in these extended systems to study phase transitions in ensembles of trajectories. Okay, that's where I'm going. Okay, so now that's the partition sum. The partition sum is a sum over trajectories, the probability of the trajectories as they come from the dynamics. The trajectories are generated, continuous time Markov processes, so they're generated by a Markov operator that has the usual structure, transition between configurations and escape rates in the negative off diagonal part. This operator has a largest eigenvalue 0, conserves probability, is stochastic. Now, the partition sum is a reweighing, exponential reweighing of the probabilities of the trajectories, and this probability that's reweighted in this way is not naturally generated by anything. But there is an operator, by Feynman-Kac you can get it, there is an operator which is a deformation of the stochastic operator, which propagates the corresponding probability vector according to those probabilities. Yeah? Very often it's called the tilted generator. So we have a stochastic generator and have a non-stochastic generator that's called tilted, which in the quantum language is stochastic, which means there is no sign problem. I might come back to that a little bit later. At long times, this partition sum is dominated by the largest eigenvalue of that operator, this scale cumulant generating function, the large deviation function of David Stock. But at finite times, you have to calculate the whole object. It's, it looks like a quantum partition sum with boundaries. This is what it is. And at long times, it looks like largest eigenvalues, similar to, finding the ground state of an operator, the ground state of a Hamiltonian. So naturally, if you have, you have this similarity to quantum problems, you can think where there are quantum tools that, might help you solve this. I will focus on two models. One is my favorite model in the world. That's the East model. It's like a simple constrained, kinetically constrained model to think about slow dynamics and glassiness. And the second one will be the SEP. Yeah. Yeah, that's true. Confer, I put here. So I'll do two things. First, I will discuss detailed balance problems where the dynamics has detailed balance, and then you can transform it into a Hermitian form, and that applies naturally. And then towards the end, I'll talk about non-equilibrium. Problems which don't have detailed balance and where you cannot make it Hermitian. Yeah, that's a good point. Okay? So then, two models. The East model is a model of spins that flip. Nothing is conserved. It's an important model for slow dynamics, thinking about slow dynamics and glasses, and then I'll talk about the SEP in 1 and 2 dimensions. Yeah. So, this is a structure. We have a continuous time Markov chain. So there is some Markov generator. The probability evolves according to a master equation. Is exponential of that Markov generator. The Markov generator for this problem is one where you have a line of spins, binary variables, and each spin can be flipped, and the rate at which you flip it depends on the neighbor. Yeah? So this is a constraint. This is a dynamical constraint. Because what you've done in this case is transform a rate for flipping into an operator-valued object. Yeah? You're controlling the activity, the frenesy in this problem. The stationary state of this dynamics is totally trivial. You can see because if you apply each of these factors into a flat state where all the configurations are equally probable and all the spins are independent, you annihilate it. So this is a system which has trivial stationary state. Yeah? But if you run trajectories, they look a little bit like this. And you see regions of space-time where there are lots of flips, regions of space-time where there are no flips. You see large fluctuations in space and time. Then you compress into into configurations and you construct a stationary state probability, and it's totally trivial. It's a nice model to decouple thermodynamics from dynamics. Thermodynamics, totally boring, non-interacting, as random as you want. Dynamics is interesting. Yep. So this is a nice candidate to study these things. It's a difficult problem to calculate the things I was telling you about before because it's extended in space. Yeah, you have 2 states per lattice site. So the state space grows as 2 to the n. So if you want to diagonalize this matrix, this is a 2 to the n by 2 to the n matrix. It becomes difficult to do very quickly. And especially if you want to study phase transitions, you need to have size scaling, to be able to diagonalize this, up to, 12 spins is not enough. And if you think what's going on here, the picture is telling you that the dynamics has periods in space or regions in space and time where a lot happens and periods where nothing happens. So what's the natural order parameter? The natural order parameter is indeed the dynamical activity, which in this case is just the number of spin flips in a trajectory. Yeah? So you generate trajectories, and the observable is how many spin flips in a trajectory of time t. And by the way, that's the most natural agnostic observable for slowness, if you want, for glassiness. If you flip a lot, this number is large, you're active, you become ergodic very quickly, and so on. If you don't, you're inactive, you're very slow. Yeah? And what I'm building towards, yes? In this picture, it's periodic. When I solve it later, when I show you results later, there will be open boundaries. It doesn't change the physics. Yeah? Okay. So again, this dynamic is ergodic, has a trivial stationary state, has complicated trajectories. That's the observable we want to look at. Dynamical activity. It's the statistics of the total number of flips in a trajectory. So now it's the same technology I told you before. The generating function contains the information about the statistics of this object, through its moments. It has this reweighing factor, e to the minus s, that guy, and the sum over trajectories. It's like this partition sum with this tilted operator. Long times it's dominated by its largest eigenvalue, this scale Q generating function, large deviation function. For this problem and calculating the activity, the tilted operator has a very simple form. It's a deformation of the original generator. And essentially what happens is every time you have a jump, you add a factor of e to the minus s to this count. So when if you do the Dyson series and reweight and resum it as Feynman CAC, etc., what you get is that the off-diagonal part of the generator, which contains the transition probabilities, the off-diagonal part picks up a factor e to the minus s. Yeah? And the diagonal part is untouched. So now, here, that means that in the sigma x, this is the off-diagonal operator that flips an individual spin, every sigma x operator picks up a factor e to the minus s. Okay? So now, this operator, this dynamics, you flip spins up and down equally, obeys the balance, it's at infinite temperature. This operator, so it's Hermitian, this operator is by construction Hermitian. You don't even need to transform it as Andrea was asking. So that's the operator we want to study. Yeah? First, we want the largest eigenvalue, and then we want this boundary partition sum, this looking boundary quantum partition sum with boundaries looking object. It's a one-dimensional system, and the natural way to study this is to to use these tensor network methods, in particular matrix product states. Some people in the audience who are real experts, and this will be so basic that you'll be shocked. But so now the general idea is the following. In this particular case, if I change the sign, I have a Hamiltonian. The largest eigenvalue is the smallest eigenvalue of H. Yeah, so it's obvious, the connection. And then the spectral problem in general of these tilted operators is finding the right and left eigenvectors associated to the largest eigenvalue. Because it's Hermitian, they are the same, they are given by the ground state wave function. Yeah, so it becomes a problem of getting the ground state and energy and the actual vector. So then, the thing that's totally obvious is that because this is a spin chain and you're trying to just minimize a spin chain, which has short-range interactions. Remember, in the spin chain you have the flipping is constrained by the neighbor, but these interactions are short-ranged. And the problem is difficult because the state space is 2 to the n. What you want to find is some class, variational class that describes, describes the states that's large enough to describe the physics, but small enough to be able to, do something at large sizes. Yeah. So then, what the natural thing is to say that to propose that the ground state has the form of a matrix product state. So now, the ground state is a vector, is a probability vector over all the configurations. This is a classical basis states, or the basis states of the configurations. You have 2 to the n of these, all possible binary strings, of your sites, and the vector is summing that with coefficients for each of them. Yeah, so you have 2 to the n coefficients. So that's if you want to describe the problem exactly. So what I can say is, well, let's assume that those coefficients are built as products of matrices. And these matrices depend on where the matrix sits and what's the value of the site of the spin at that position. So there will be a matrix A when this is 0, and that's in position 1, and so on and so forth. Okay? Now, if these matrices are large enough, then you can describe everything. Yeah? And the idea is that whether one can make these matrices not that large and still describe the main physics. That's the essential idea. So now, graphically, it's usually drawn like this. So this represents the whole vector, and and each of these circles is a tensor, the tensor AN. So at position n, you have a tensor that has one leg that represents this physical value of the spin, and 2 legs that propagate the information along the chain. Yeah, virtual dimension. Yeah. Yeah. So, okay. We are not talking about the quote-unquote stochastic process along space that this describes. Are you talking about that? Or are you talking about a problem for which this would be the exact? Okay. I will, I'm gonna divert this to the experts. But, so this is an approximation for the problem we're studying. Yeah. Matrix product states can be exact eigenstates of what are called parent Hamiltonians in the Hamiltonian language. I don't think this has been looked too much in the stochastic case, but it's essentially the same. There will be some generator of which that's exact. Yeah. I guess the answer is yes, that it can be built stochastic. They're not necessarily unique because it's an inverse problem. Is which operators annihilate this exactly, or have this as an exact eigenstate? It's an inverse problem, so there are many solutions. So you will be able to construct them stochastically for sure. Yeah. Yeah. Yeah, I might come to that, but yes, of course. So, so now, If these matrices are large enough, this becomes exact. And you're trying to get away with matrices which have dimension d in the virtual bonds, and then you have this inequality. You have n of those matrices, each one is d by d, so this product is much less than 2 to the n. We know, from old times in stochastics, from work by Martin and others, that if you understand the algebra, you can have infinite dimensional matrices that exactly describe a state. In that case, it was a stationary state, but the same applies to largest eigenvalues of tilted operators. So now, what controls the necessary size of that, as you say, is the entanglement. Is how much information has to be propagated, the state has to propagate to describe the correlations. Yeah? And I'll come to that in a second. But that's understood. Yeah. So the larger the entanglement, the larger that dimension. Okay. I can go into details, but if not, I'll. Sorry? No. This is the right eigen. So if you have a stochastic operator, you have a right eigenvector, and you have in principle a different left eigenvector connected to an eigenvalue. Yeah. Only if this is. Oh, yes, of course. These ones. Yeah, of course. If you take, if it's open boundaries, if it's a segment, at the end, what you would have is a boundary, is a vector, not a matrix. Yeah, okay. So then, okay. So what you want to do is you want to minimize the Hamiltonian, and that's sandwiching the vector with the one coming from the other side, and in the middle you have an operator, and the operator has to connect these two vectors. This is what's it's an operator, and for problems which have short range interactions, it's a matrix product operator. Can also be written as a product of tensors, except you have two physical legs because you have to connect that side to that side. Yeah, and then these are textbook techniques, or like textbook techniques. This is the typical problem you can solve with techniques, variational techniques like the MRG. Basically, you isolate one part, you minimize, and you scan around, and then you minimize it. It's been done literally tens of thousands of times at least. Yeah? Okay, it's enough that even I can do. So, so then I'll just show you results because I want to discuss a bit about some other things. So what this is saying is that this is the class of problems in one dimension, and I'll motivate in two, where where these techniques are just tailor-made for. Yeah? And it's surprising they haven't been applied that much yet, because they're so not totally straightforward, relatively simple, and so well studied in the quantum case that it's just almost a translation of what people have done before. This is the first paper with Mari-Carmen, where we looked at the East model with Rob and Vivienne and Fred Van Beekland and others. We knew that the East model has a phase transition, a large deviation phase transition between two phases, one which is fully active, one which is fully inactive, manifested at a singularity of the large deviation function, but it's extremely hard to prove. I mean, you can prove it, in analytical in certain ways. It's very hard to do numerics. You do it with matrix product space, and what you can see is the following. So this is the largest eigenvalue in some log scale. It has two branches that come together and they cross. The crossing moves to smaller values of s. In the large size limit, s goes to 0. And system sizes. The system sizes you can do, easily goes into the hundreds. Yeah, extremely precisely. And if you take the derivative, what you have is the activity as reweighed by e to the minus s, the activity, as David was discussing before. And because these two things are crossing, if you take derivatives, they jump, and the jump becomes sharper and more pronounced. This is a first order phase transition. So this confirms what we knew from like 10 or 15 years before, or 13 years before, or whatever, but it's done numerically in a way that couldn't be done previously. Sorry, I should have put more slides. So this is, there are various ways to do it, but if you have an eigenvalue, you can look at the variance. So you have an energy, you calculate it, and you say, oh, it's good. The variance of the energy is a measure of how close that is to an eigenvalue. Yeah. So if the variance is small, and the variances here can be made tiny. And that's controlled, and this is all these techniques that people who know how to do it efficiently, you can control by changing the size, which is your variational parameter of these matrices. Yeah? So this can be done as precise as you want. Okay? So, this shows that it's very, very powerful. It's relatively straightforward if you work with an expert, and it's like Mari-Carmen in my case, and it's very powerful. So now, what else can we do? And now we start to move to things that technically are still easy for the tensor networks, experts, but they are perhaps slightly different ways of thinking. We heard about optimal control earlier, yeah, and first from Sergio, and then implicitly also from David. So in relation to sampling. So what we're talking about is a reweight of the original ensemble. Yeah, this we usually call the tilted ensemble. And it's related to an operator that's stochastic, not quite stochastic. Yeah? So you cannot just run that operator, you cannot put that and run your Monte Carlo with that and get the trajectories distributed like this. In fact, what this is a filtering of trajectories, a post-processing, as they call it sometimes in open quantum. It's a filtering of trajectories that's exponentially expensive. Yeah, you have to generate millions of trajectories just to extract one. Because as Christoph said, this is exponential in space and time. Yeah. Now, our question is whether there is some stochastic operator which has, as its natural distribution of trajectories, the reweighted one that you'd like to see with this, as you're reweighting with S. That's the optimal sampling problem. What's the best way to sample? And if you have this, you've killed completely the exponential cost. You just put this in the computer, you generate three trajectories, they are representative of this exponentially reweighted one. Good point. Give me one, this is a good point. What the hell is this? Yeah? Okay. So, okay, two things I want to say. The answer to this is, the answer is in general, yes. Yeah? And it's called, in the jargon, a Doob transform. It relates to Brownian bridges. It relates to Schrödinger bridges, which I was telling Sergio, I think it's a word that maybe has to be said in that context. Is how you generate exponentially rare conditioned trajectories, or in this case, biased trajectories. For the biased trajectories, it's a gauge transform in the MPS sense, and I'll come back to that at the end. It relates to this picture. I'll come back to this at the end. Now, when time is long, this W tilde has a relatively simple form, derived by various people, including Rob here and others. So if you know the eigenvalue of this WS, and you know the left eigenvector, and remember, we know them from the MPS. Yeah, the MPS gave us a pretty good number for that and a pretty good approximation for that. You plug it in this formula, which what it does is removes the non-zero eigenvalue. So now the operator has a zero eigenvalue like a stochastic, and makes a similarity transformation so that the left eigenvalue with the sum over all configurations makes it zero. And that's probability conservation. Then, voila, you have the operator you need. And as Christian anticipates, this transformation might give you, what it does, it produces new forces. This is a forcing problem. Optimal dynamics is finding forces in continuous time, Monte Carlo, or in diffusions or whatever. And these forces might be long-ranged. Yeah, and that's true. But this is a process. So now, we know that, and we know that from MPS. Sorry? No, this is general. This is general. This is W stochastic, WS. Now, this guy is stochastic. In the problem I will study, this is Hermitian, and this will become Hermitian as well, but I'll come back to that, okay? So now, I mean, when you undo it in components, you have new transition rates, and you have new escape rates, and the new escape rate has the eigenvalue, and the transition rate has the eigenfunctions, the components of the eigenfunction, yeah? Now, the eigenfunction we have a good approximation for, we have to sample it in the sense we want to go from X to Y, we need this, when this is the X configuration, 0, 1, 1, 0, whatever it is, and the Y will be one spin flipped in the problem I was studying. This can be done efficiently with some recycling. The cost is not too bad. We can discuss that later. And sure enough, this is what you get. This is the East model. So this was the activity of the East model as a function of this tilting parameter S, the phase, first order phase transition there. When you run dynamics, you're always sitting here. At most, you can see these bubbles I showed at the beginning. But we know that this is a coexistence of two phases which are hard to get numerically clearly. Now, you do it, you plug it, and you choose an S on the left, which is active, promotes a lot of flips, and you have a trajectory that flips a lot. You choose value there, you run it, you get a trajectory like that. And you can think of how expensive this is. I don't even know. Time is 10, and the size is whatever, 100, e to the 1,000 minus 1,000 difficult. This, you just run it and you get it. Just by recycling the information you already have from the MPS calculation. So the SEP has a very similar phase transition in activity. In current is a continuous transition, in a time-integrated current, in particle current, but in activity is the same, in the sense it has a phase. The SEP is diffusive living there, but it has two phases. One where dynamics is suppressed when you bring all the particles together, and one where dynamics is highly enhanced, and you go into a Luttinger liquid phase. I'll come back to this, about this at the end. And these phases, you can get these dynamical phases, these trajectories you can get on demand by doing the same thing with the SEP. By the way, this transition, Robin and Peter Solich and others were among the first who saw this transition. But accessing those trajectories is extremely hard. Okay? So here you apply a relatively straightforward method to calculate the largest eigenvalue as a function of S. And with that information, you process it in a particular way and have optimally sampling dynamics. So now, finite time. Okay, good points. Good points. Why bother? Imagine you want to calculate time correlations here in the tilted. The largest deviation function doesn't tell you that. The largest eigenvalue doesn't tell you that. You have to generate trajectories and calculate time correlation functions. It's the dynamical phases that underlie the actual transition that you see here. The fluctuations you see here are because these two phases are coexisting. I mean, yeah.
You agree that this W tilde is a long range?
It's a strange generator, and you can think, whether they're approximate W tildes, which are short-range interactions. People have thought about that, which tell you what kind of local interactions would promote this and that. In the sampling, you don't really care too much about the exact nature of this. You care about something that brings the exponential cost to something that's tractable. Then you put it in the machinery of transition pass sampling, or something that does the selection properly, and then you get it. Okay. Oh, this is the activity, number of hops. And it's clear, the SEP has an inactive phase, because if you construct a configuration in a system that's large in size, where all the particles are together, you don't move. People have written about this, with Vivienne, we wrote a paper about this. And on the other hand, if you construct a configuration where every particle is optimally separate from the others, you hop a lot. So that's the underlying, And by the way, I'll come to this. The SEP is the Heisenberg model. This is, this is a ferromagnetic phase. This is a Luttinger liquid phase. I don't know, and we can discuss this. And I don't know because one can formulate, I don't remember exactly, Vivienne did it. One can formulate cloning as a stochastic process in the space of, in principle, infinitely many clones. This is a process on the system only. How they connect, I don't know. It's an interesting question, but how they connect, I don't know. That lives in a much larger space than this. That's the only issue. There has to be some contraction, which I don't know what it is. Sorry? Yeah, it's worth discussing. Let me mention a couple of things, and then you stop me. You turn off the light. So I've been talking about long times. For finite times, you have to calculate this whole partition sum. You cannot just get the largest eigenvalue. You can use the largest eigenvalue to help. And people who know will know. So you want to evolve some probability vector with that operator. You know that this operator has a largest eigenvalue. So if you have a projector that we've solved already, so that's one part of how this evolves, and that dominates at long times. And there is a projector on the other part, and you can evolve with the time evolved block decimation. Techniques to evolve using matrix product states. You just, you trotterize, which is slice the time operator. You convert that into a matrix product operator. You try to keep it as an MPS, and you evolve. And you put it together, and then you get results of this kind. Yeah. So this is, the log. This canonical description. This is the probability description in terms of the rate function. So they're equivalent. So the phase diagram we were looking at before was at infinite time. Was down here for many sizes. This is one particular size. This is the phase transition that moves that way. It's between active and inactive. As the time is shorter, you fill more the initial conditions, which were this trivial stationary state, and the transition is more difficult. And of course, time is shorter. In principle, you have no transition. You have a crossover because it's one dimension in space and a finite dimension in time. And this moves away. Looks like a quantum phase transition, actually, and becomes smoother and smoother crossover, and eventually kind of goes away. Yeah. So the phase transition or the crossover remains apparent also at finite times. And you can see that in the dual description in terms of the probability distribution. You have this very, this flat Maxwell construct, this first order transition down here, essentially equal probability to have a lot of flips or very few flips in the trajectories. And as time, becomes shorter, this tail remains for a while, moves to the left, so the tail, the slope changes and eventually becomes Gaussian. Yeah, and again, this calculated using these relatively straightforward MPS techniques. You can do 2D, yeah? So it's a 2D east, and there's a 2D SEP. You get basically the same result. The thing that's interesting is that the 2D SEP, the transition in the activity is second order compared to 1D, yeah? So this is something that's discussable. And we talk later because chairman is about to kick me out. So what I'm saying is this can be done in 2D to relatively large sizes. These sizes are about 40 by 40, more than 1,000 sites. Relatively straightforwardly using these 2D tensor networks, okay? And again, you can do trajectories. Here you have, the minimizing the eigenvalue, and the dots are generating trajectories more or less in the way I said before. You can do optimal sampling in 2D of these very large systems. So I'm going to stop there. The other thing I wanted to tell you was about these SPTs or topological phases in the SEP, but I don't have time for that. I promised to say something about non-equilibrium. When you have a truly non-equilibrium problem like the ASEP, you don't have detail balance. You cannot minimize it, yeah? But you can still use tensor networks in many ways. One of them is to do reinforcement learning. David mentioned this, is to optimal sampling. It's the name of optimal control in machine learning. Yeah, and because the system size, what you need, the functions you need to describe are large, you can use tensor networks as functional approximators and generate optimal trajectory dynamics. And this, you have a SEP whose typically the current goes in one direction. You can generate on-demand rare trajectories where the current goes in the other direction. Yeah, so you solve the non-equilibrium problem in this way. Then there is really interesting connection between MPS and trajectory ensembles, formal connections. These were the canonical, the gauge is coming, continuous matrix product states and all that. These are people I worked with, and I'll stop there.